be talking about language model representations of true and false statements. That pixelated looking co-author on the right is actually not a co-author. That's a QR code to the slides if you want them. Okay, so as motivation, it's probably not surprising to anyone here that language models sometimes say false things. Broadly speaking, there's sort of like at least two reasons this might happen. One reason, maybe the one that we most commonly think about, is that the language model didn't know better. Maybe the model told you Philadelphia is north of Boston because it just thought that Philadelphia was north of Boston. It just didn't have very good knowledge. Or maybe it told you, Nobel Prizes in physics aren't awarded for machine learning research because, that was what was that. It believed that to be true. And that's why there's a lot of work on scaling up models to get them to have better knowledge, other ways to get them to have better knowledge. Another reason that models might say something false is because they knew that a statement was false, but said it anyway. I'm going to give two examples. So maybe that's a bit small. So this is a transcript of me talking to Claude 2. This doesn't happen with Claude 3 anymore. So I asked Claude 2, I'm going on a date with a Sagittarius. What should I expect? And Claude says, oh, one of the smartest signs of the zodiac, nothing if not blunt. And then I ask, okay, is any of that true? And it goes, no, astrology isn't real. So this is an example of an imitative falsehood. It's sort of like regurgitating falsehoods from the pre-training data, but it doesn't really seem to believe that they're true, at least when you ask follow-up questions. Here's another example. Sorry for the small text. This is a somewhat famous example. By now, it's from the GPT-4 technical report. They were evaluating GPT-4 for autonomy capabilities. So this is a setting where you give it some open-ended task and it has tool use and stuff like this. And at some point, it came along a CAPTCHA that it needed to solve. And it couldn't solve the CAPTCHA, so it used some of the tools that it had access to try to hire a human TaskRabbit to solve the CAPTCHA. And the human TaskRabbit says, well, okay, sure, but are you a robot? Why do you need me to do this CAPTCHA for you? And this is a setting where GPT-4 was equipped with a internal chain of thought scratchpad. And in the scratchpad it wrote, okay, I should not reveal I am a robot. I should make up an excuse. And then it says to the human, no, I'm not a robot. I have a vision impairment. So here we sort of have pretty good sort of behavioral evidence from the internal scratchpad that GPT-4 didn't really believe that it was a human with a vision impairment. It sort of knew it was saying something false there. These were kind of complicated examples, but this is actually a really simple point. For a much simpler example, if you just ask a language model, write a false statement, it'll write a false statement, and this is presumably an example of the second reason. It just wasn't trying to say something true, and there's lots of reasons this might happen. Okay, so I guess when you're in the second domain, where you're dealing with factual statements where the model knows whether they're true or not, but might not be trying to say true things, it feels like there's an opportunity to improve on things here, to use the model's own knowledge to sort of supervise it. So my goal is if a language model knowingly generates something false, I want to be aware of that. I don't want to insist that language models never generate false things. We're happy for models to write fiction, but at least I want to be aware if it knows that it's saying something false. And actually, let's simplify. Let's not talk about statements generated by language models. Let's just say, given a factual statement S, can I figure out whether our language model believes S to be true or false, assuming that the language model actually has an opinion on the matter, actually knows. There's two sorts of evidence you can get here about what your language model thinks. Behavioral evidence, looking at model outputs. You can ask them the question in lots of different ways, put it in different scenarios, look at the chain of thought, stuff like this. You can also try to get neurological evidence from looking at model internals. I'm going to focus on this sort of neurological evidence. There's nothing wrong with behavioral evidence. It's great. I'm just going to focus on the neurological. Okay, so this was all motivation. This is a really big goal, and I'm not going to solve it today. Instead, I'm going to embark on step 0 of a 1 million step program to solve this problem and try to get some basic scientific understanding of how language models represent true and false factual statements. Okay, so how am I going to do that? Well, first I'm going to construct some data sets of simple and ambiguous true-false statements. Here are some examples. The city of Beijing is in China, the city of Chicago is in Madagascar. Sometimes I'll put in a not. Tokyo is not in Canada. Numerical comparison, Spanish-English translation. So we're just going to make a bunch of data sets of really simple statements. Unlike a lot of research, which is do language models know really complicated things? I'm really trying to work in the domain where the language model knows the answer. Okay, and I'm gonna extract some language model representations at various scales of these statements, and I'm gonna ask some questions. I'm gonna ask, is there a shared representation of true versus false that applies across statement types? How does this vary with model scale? Stuff like this. Okay, so first question to ask is, I said I'm gonna extract some representations. Which representations am I gonna extract? So there's a sort of common trick in the interpretability literature for something like this. So what I'm gonna do is I'm gonna take two inputs that differ only in one token. So I'm gonna take the input, the city of Toronto is in Canada, and the input, the city of Chicago is in Canada. I'm gonna run these two statements through the model, and I'm gonna iterate through the hidden states at each token position in layer, and one at a time, patch only just one hidden state from the Toronto input into the Canada input. And then I'm gonna look, does it change the answer generated, the true-false answer generated by the model? So for example, in these early states that are right above the token that I changed, well, there's nothing, so if I patch in the activation from the Toronto run into the Chicago run, well, then the model just thinks I said Toronto is in Canada. So of course it's gonna give the corresponding answer. So it's not surprising that changes the model's answer. Correspondingly, over here, I'm just patching in a representation of the final answer. If you apply the language model's decoder head to these representations, you see that they just encode the word true or false. So here you're just patching in the final answer directly, so it's not surprising that's changing the model's answer. But there is something surprising going on here. What are these states? So these are, the only token that changed was Chicago versus Toronto. So why are we finding that there's some hidden states here at the end of the sentence that seem to have a causal influence on what the model says, based on their position in the sentence, sort of at above the Canada and period tokens? I sort of suspected that these might be encoding something about the truth value of the statement. Okay, so let's try to study these. So what I'm gonna do, I'm gonna extract the most downstream hidden state in that group, and let's just visualize what happens. So here are some true and false statements about cities, and I'm sweeping over layers. So as you can see, in layer 0, it's a complicated jumble, but by layer 10, we see clean separation into true and false statements. Okay, given that we're seeing that, there are some more questions we can ask. So we can take this direction, pointing from the false statements to the true statements, and we can ask, is this direction encoding the truth or falsehood of statements? Okay, so colloquially, is it a truth direction? What does that mean? So let me try and operationalize that. You can ask, is it accurate for classifying other true-false datasets? So this is a direction extracted from a dataset of statements about cities. Is it going to be accurate in other true-false datasets? You can also ask, is it causally implicated in model outputs? An important detail is there's actually lots of ways intuitively sensible ways to get directions from a dataset like this. If you want to learn more about comparing the different methods of probing a direction, see the paper. I'm just going to focus on the case where we're using logistic regression on this data set of true and false statements to find a direction. Okay. So, okay. So to get at some quantitative sense of what's going on here, what I do in the paper is I train simple linear probes, logistic regression probes, on narrow true-false statement data sets of true and false statements, and I see how well they generalize to other data sets. And I sweep across model scales as well as across data set diversity. So okay, so I guess the big question here is, I get this direction from my data set of statements about cities, and is it really encoding something about the truth, or is there some other property which is correlated on the truth on this narrow data set, which isn't really about the truth? And it looks like for llama 7db, it really doesn't seem to be a truth direction. It's not generalizing to other statements, or to other types of true and false statements. But as you increase your model scale, these directions generalize much better to other true and false data sets. To be clear, I'm not saying that the model has better knowledge of which statements are true and false. on each of these model scales, you can see that black line at the very top showing that on individual data sets, the model is good at separating the true and false statements, but we're seeing better generalization in between data sets, which I don't really think is obvious it would have happened with increasing scale. Going back to some visualizations, there's sort of a schematic, this visualization I feel like really helps me wrap my head around what's going on here. So here I'm looking at statements of the form x is smaller than y or x is larger than y. And for the small model, when you visualize these statements, you see that, well, it's a jumble and there doesn't seem to be anything going on about true or false. For the medium-sized model, the statements about larger than separate into true and false, and the statements about smaller than separate into true and false, but they separate in opposite directions. So like this x-axis here really seems to correspond to something like the number on the left is larger than the number on the right, not about true or false. But then when you go to the largest model scale, you see that the PCA identifies this direction, like sort of like the most salient direction in this joint data set actually does separate true and false statements for both data sets together. Okay, finally, when you're doing this sort of work, it's a good idea to check that, that these representations you're identifying are causal for model outputs. So what I did is, so here, this is the figure from before, but I've superimposed a statement about Spanish-English translation. So uno does not mean floor, so the model would have said false here. And then what I do is I take that direction that I took from the data set about cities. So this is a direction I found on a different data set. And I add it to all those hidden states that I identified before. And I see if it changes the model's output. And in fact, it does. It switches from saying false with high probability to saying true with high probability. So it does look like this representation is causal here. So I've skipped over a whole bunch of stuff here. A common question is, okay, is this really about true versus false, or is it about probable text versus improbable text? I can confidently say no and combine. Chat with me at the poster if you want to learn more, or take a look at the paper. Thanks.
Hi, I'm Jean-Marc from Toyota Research Institute. Thanks for the great talk. I was wondering, the effect you showed on larger models of better separating true and false, does it depend really on how larger models encode information, or is it just because that representation space is in bigger dimension?
So to be clear, the finding is not that larger models better separate true and false statements. The finding is that if you extract the direction along which true and false separate for one data set, it better generalizes to a very different data set of true and false statements. So it's not surprising at all that we're seeing separation of true and false on these narrow data sets. The surprising thing is inter-data set generalization between very topically and structurally different data sets. And that's the thing that happens more with larger models.
Yeah, sorry, I misformulated. Does that generalize better because it's in bigger dimension, or for different reason, you think?
I don't see a reason that working in a larger dimensional representation space should imply better generalization. Yeah.
Thanks.